Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series meant for optics, and we are nearing the end of this section which deals with diffraction. This particular phenomenon of diffraction is of great importance. Maybe today, if in Indian Space Research Organization or as far as the country is concerned, if Mangalyaan goes into the Mars atmosphere, and when they want to detect the elements present in the Martian soil, we make use of the phenomenon of diffraction. That is, Xxxvi diffraction is used to determine the elements present in the Martian soil. So this day is an important day in the space history of our country. So today we are talking about diffraction of light beam. Whatever we say, the general theories, they hold good for any kind of diffraction, whether it is Xxxvi diffraction or neutron diffraction or electron diffraction or proton diffraction or ordinary light diffraction. The contents of this lecture are as follows: distinction between Fresnel and Fraunhoffer types of diffraction, diffraction at a circular aperture, diffraction at an opaque circular disc, and we will be going through in the lectures to come diffraction at straight edge, wire, and so on. Anyway, the basic principles are the same, and let me briefly recap the differences between Fresnel diffraction and Fraunhofer types of diffraction. The diffraction phenomenon or phenomena in general are broadly classified into Fresnel diffraction and Fraunhofer diffraction. In Fresnel diffraction, the source of light and the screen are effectively at finite distances from the obstacle or the object. The obstacle may be a circular aperture or a straight edge or a blade or any kind of object, or maybe a thin wire whose diameter is to be determined. So diffraction taking place in these materials, they come under Fresnel diffraction, where we will not be making use of any lens. Observation of Fresnel diffraction does not require any lenses. On the contrary, you look at the right hand side, that is the Fraunhofer diffraction. So far I have been talking to you about Fresnel diffraction. I told you in Fresnel diffraction we don't require lenses, and you have got your object, the source of light, and the screen, they are at finite distances. Okay, the obstacle may be placed here. Here I have shown the slit through which light is passing, and when the light is passing through a narrow slit, it suffers diffraction. On the other hand, you come to the Fraunhoffer diffraction, wherein the light is supposed to be at infinite distance from the slit, and the screen also will be at infinite distance from the slit or the wire, whatever be the thing that you are keeping here. And in order that the light rays are made parallel, you may be having a condensing lens. You got a lens here, and similarly, in order to get a point image or a line image, you want to have the image on the screen, you got another condensing lens here. Therefore, the lenses will come into the picture in the case of Fraunhoffer diffraction, and also, as I told you, the distances concerned will be infinity, unlike the case of Fresnel diffraction. The incident wavefront is not planar, in which case I am talking about the Fresnel diffraction. The incident wavefront is not planar. As a result, the phase of the secondary wavelets, they are not at the same points in a plane of the obstacle. The resultant amplitude at any point on the screen is obtained by the mutual interferences of secondary wavelets from different elements of unblocked portions of the wavefront. We will go into the details later, and in the case of Fraunhoffer diffraction, the source of light and the screen are effectively at infinite distances from the obstacle, as I told you earlier. Secondly, the pattern can be easily observed in practice. The conditions required for Fraunhoffer diffraction are achieved using two convex lenses, as I showed you earlier. Again, a lens is used to make the light from the source parallel to the obstacle, and this light which suffers diffraction or experiences or undergoes diffraction at the slit or any other obstacle will be made to come to a focus using a second lens. Therefore, you will have two lenses. That is what I am trying to tell you here. The incident wavefront as such is plane, and the secondary wavelets which originate from the unblocked portions of the wavefront are in the same phase. This is the important point, or in the same phase at every point in the plane of the obstacle. This problem is simple to hand mathematically, that is the Fraunhoffer diffraction, because the rays are made parallel by using a lens. The incoming light is rendered parallel using a lens, and the diffracted beam is focused by another condensing lens, as you saw in the picture. The diffraction problems which are dealt with hereafter, they are all coming under Fresnel class. This is the point I want to emphasize is the diffraction phenomena which we are trying to understand, or which will come across in the lectures to come, will fall under Fresnel diffraction. Now, we will go to the problem of diffraction at a circular aperture. What do you mean by aperture? Aperture is nothing but a hole drilled on a cardboard or on a metal plate. You have got a light beam here, you have got incident light that is coming and passing through a hole. The radius of the aperture or the radius of the hole is r, and you have got the diffraction pattern on the screen. You have got a screen here, right? This is what you call as the diffraction at a circular aperture. More or less, the summary is as follows. You have got an incident beam coming and passing through a hole leading to a diffraction pattern. A diffraction pattern that you have got here in the case of a hole is made up of a bright region followed by dark region, bright region, dark region, and so on. Okay, this is something like what you have seen in the case of Newton's rings, and that is the one that you came across in the case of interference. But here is a question of diffraction. The point I want to tell you is the intensity changes. You see, the intensity here is maximum, then you got dark and maximum intensity, darkness, and so on. So you got a diffraction pattern where the intensity will be changing. Now, how will you explain the change in the intensity? Now, in the case of interference, we explained the changes in the intensities because of maybe constructive interference, wherein a crust meeting a crust will lead to brightness, or a trough meeting a trough again will lead to brightness. On the other hand, a crust and trough will annul each other, giving a darkness at a particular point. That is a destructive interference. In the case of interference, what I am telling you now. But in the case of diffraction, you should bring in something else into the picture in order to understand the intensity variations. What we have done earlier is when you have a wavefront which is incident here in this region, when a wavefront is incident on the hole or on the slit or on a wire, the incident wavefront will be divided into number of half period zones, without which we cannot explain intensity variation in the diffraction pattern or the intensity variation that you observe on the screen. So, what you do is you have got a source here, the wavefront that is incident at the point O. What is O? O is the point corresponding to the aperture. It is nothing but a hole, a fine hole through which light is passing. That gives rise to a pattern of this kind. We want to understand, or we want to explain as to how you are getting a pattern. That is the objective before us. For that, what we are doing is the wavefront, the light beam that is incident here, or the wavefront that is passing through this aperture is divided into number of half period zones, as we did earlier. Why should you divide it number of half period zones? Why they are called half period zones? Because the very words half period means there is a time difference between the light beam coming from the first zone and the second zone. What is the time difference? Half period, T/2. That means if a crust is coming through the first one, a trough will be coming from the second. Again, crust will be coming from the third. Therefore, 1 and 3 can be or should be added, because crust means the crust. But 1 and 2 will be annulling each other. They will be fighting against each other, because crust and trough. Therefore, there will be a time difference of T/2. That is the reason why they are called half period zones. A time difference of T/2 will refer to a phase difference of pi or a path difference of λ/2. Okay, you should be able to tell how much, what is the time, what is meant by half period zone. Why it is called half period zone? Because the light coming from successive zones will try to annul each other, whereas light coming from alternate zones will be adding each other. The amplitudes will be added up, or the intensities will be added up. Okay, those things we will be doing in the lectures to come. Therefore, you got AB is the wavefront incident on a small aperture. It is a pinhole, as I told you, and S is a point source. So, the detailed description of what is going on in the case of light going through circular aperture. You all know by circular aperture, what we mean is a hole, light passing through a hole, which is giving rise to a pattern, a diffraction pattern, and we want to understand the diffraction pattern. As I told you, the diffraction pattern we will try to apply on the basis of half period zones. So, let us now look at the wavefront, then we will divide the wavefront into half period zones. So, AB is the wavefront, incident on a small aperture, and S is a point source, which you will see on the left hand side. Xy is the screen kept on the right hand side. You got a source here, then you got a fine hole drilled on a plate or a cardboard, light is passing from the source through the aperture, and it will be, the pattern will be obtained on the screen. Supposing you assume light to follow the Newton's ray concept, then because light is passing, there is a hole, then you will be having only a point with a finite intensity. That is what you will be getting if light travels in the form of straight lines. But we say that light is traveling in the form of waves, and again light is undergoing diffraction. Because it is undergoing diffraction, you get a pattern that you have got, the intensity is not uniform, you get darkness, brightness and so on. So what we are going to do is, you have the distances. SP is perpendicular to the screen, O is the center of the aperture, O is the center of the aperture, R is the radius of the aperture. These things you can see here. So S is the source and O is the center of the aperture. The distance SO is equal to A, and the distance that separates the center of the aperture O to the screen Xy, from O drop a perpendicular, OP is there. The distance OP is B and is A, and you got QQ1, the wavefront incident on circular aperture. Now what we are going to do is, this wavefront will be divided into number of half period zones. Where is the aperture? I am not showing the aperture because a tiny hole. So I will show in the diagram to come the aperture. You see the aperture, there is a small hole here. So you should have a small hole through which light should be coming, and the intensity will be obtained at P, and we will first try to explain the intensity at the point P, and then we will try to understand the intensity at point P prime, which is far off from the center of the, you got O is the center of the aperture, and the OP is the perpendicular drawn. So P is the point here, straight in line with the source. You have to go to a point like P prime, which is far off from P. As I told you, we will try to calculate the intensity at P as well as P prime. First we will discuss what happens to the intensity at the point P. Now as I told you, you have the the wavefront is here. The wavefront is divided into number of half period zones. Can you recall how the half period zones are constructed? How did we construct the earlier lectures? You have O is the pole and P is the point, and with P at the center, you have draw spheres with radii what? B plus lambda by 2. You know, lambda is the wavelength of the monochromatic source. You got a monochromatic source. So with P at the center, draw spheres with radii B plus lambda by 2. Lambda by 2 means that is the edge of the first half period zone. Then B plus lambda by 2. Then the next zone B plus 3 into lambda by 2. So in short, you have the first zone is obtained by drawing a sphere with P at the center. The radius of the sphere is B plus lambda by 2. The second is B plus 2 into lambda by 2. 2 into lambda by 2 is lambda. So B plus lambda is the radius. Then the third one will be B plus 3 lambda by 2. The fourth one will be B plus 2 lambda. So you have with P at the center, draw spheres with B plus lambda by 2, B plus lambda, B plus 3 lambda by 2, B plus 2 lambda as the radii, and draw the spheres. And these spheres will cut your QQ1 and will give rise to circles. The cross section will become circles. The wavefront, I told you in the earlier lectures, the plane wavefront will consist of a number of zones. We talked about zone plate also. So it's a plate or a plane in which you will be having the first half period zone, second half period zone, third half period zone and so on. Okay. So similarly here, now this AOB will consist of first half period zone, second half period zone and so on. So for the first half period zone, the distance will be B. For the second half period zone, the circumference of the first half period zone will end at B plus lambda by 2. Now supposing you have the aperture will allow only light coming through the first half period zone. The light coming through the first half period zone, what will be the amplitude of the light? That is M1. Second is M2. Third is M3. As I told you, the light coming from the first half period zone should be summed up with the third, fifth. You have to talk of odd and even zones. Two successive zones will annul each other because there are time difference t by 2 or a phase difference of pi or a path difference of lambda by 2. If light is allowed by the first zone, a crust will be coming, second will have a phase lag of pi. That means a phase difference of pi means what? A crust is coming, trough will be coming. They will annul each other. They will try to destroy each other. Therefore, if you have got 5 zones, the total intensity or the displacement will be M1, then minus M2, then plus M3, then minus M4. So the alternate zones will be opposing. Therefore, you should have a negative sign. Now let me come back. If the first half period zone has a diameter such that it allows only the first zone, the displacement will be M1. So the intensity will be M1 square. Therefore, I will now come to these points now. Your SO is equal to A, OP is equal to B, these things you know now. QQ1 is the incident spherical wavefront, and with reference to the point P, O is the pole of the wavefront. O is called the pole of the wavefront. To consider the intensity at the point P, as I told you, the point P, I will come to the P prime later. At a point P, you want to calculate the intensity. What you do now? You construct half period zones, right? With P as center, you draw spheres. What are the radii of the spheres? As I told you, B plus lambda by 2 and then B plus 2 lambda by 2. 2 lambda by 2 is lambda. Then the next will be B plus 3 lambda by 2. Next will be B plus 4 lambda by 2. So with these as the radii and with P as the center, draw the spheres. These spheres will give rise to circles on a 2-dimensional thing. I am talking about 3-dimension. I got a 3-dimensional sphere. You got a plane. On the plane, they will make only circles. So the first circle with B as the radius, the first circle will be the first half period zone. With B plus lambda by 2, that will be the starting of the second half period zone. Then the third half period zone. So the light coming from the first half period zone will have the displacement M1. I am going to now talk about, depending upon the distance of P from the aperture, that is the distance B, the number of period zones that can be constructed may be odd or even. If the distance A is such that only one half period zone can be constructed, that means light is allowed. Only one half period zone is there. That means the aperture consists of only one half period zone. Then, as I told you just now, the displacement will be M1. The intensity will be, what is intensity? It is square of the displacement. Then, as I told you, then the intensity at P will be proportional to M1 square, where M1 is the amplitude due to the first zone at P. Therefore, if the aperture is such that radius of aperture or the hole is such that it will allow light that will be passing through the first half period zone only, or the circumference circle is equivalent to the area of the first half period zone, light will be passing through only the first half period zone. The amplitude of light will be M1. The first half period zone will produce amplitude M1. The second will produce M2, M3 and so on. Now you should be able to comment about M1, M2, M3 also. Now what is the comment you will make? We talked about the obliquity factor. You got the first half period zone here, the second will be here, the third one will be here. So this is the point where we want to find the intensity. The angle subtended by the point with respect to the first zone, second and third, the angle subtended will keep on increasing. So because the obliquity factor we saw in the earlier lectures, the intensity will decrease. So the comment which you have to make is the following: M1 is greater than M2, M2 is greater than M3, M4 and so on. So the amplitude of light coming from the first, second, third, fourth and so on will be such that M1 will be greater than M2, M2 greater than M3, M3 greater than M4. As the zone number increases, the displacement cost or the intensity cost at a given point will decrease. These things ought to be kept in mind because of the fact I will be making use of these factors in the calculation when you go to the point P prime. Now we are concerned about the point P. We assume that light is coming only through the first half period zone. The light coming from the first half period zone will give rise to amplitude M1. The intensity will be M1 square. Therefore, the intensity at the point P will be proportional to M1 square. On the other hand, if the wavefront is exposed to the point P, the resultant amplitude is M1 by 2, or the intensity at P will be proportional to M1 square by 2. The position of the screen can be altered. The screen position can be altered to allow the second and third half period zones. The position of the screen can be changed, and if the aperture is such that light is passing through not only the first half period zone, second and so on, then in such a case you have to take into account the resultant M1 minus M2, as I told you, M1 minus M2 plus M3. And so when we talk about light passing through if the aperture is to allow light to pass through in such a way through number of period zones, then things are different. I will come to that in the next lecture. And now let me pass on to the summary of what I did in the present lecture. The summary goes as follows. The problem of diffraction at a circular aperture or a circular disc or any other obstacle is to be treated on the basis of the fact that it has to be divided into number of half period zones. The intensity at any point depends upon the odd or even number of zones which are allowed. The intensity also depends upon the obliquity factor. We will now pass on to the question session, and the questions are: what are the differences between Fresnel and Fraunhoffer types of diffraction? Then how does the intensity at any point depend upon the odd or even number of zones? The question number 3 is: what is obliquity factor? What kind of diffraction pattern do you get on the screen in the case of a circular aperture? With this we come to the end of this lecture. We will continue with the rest of the things in the lectures to come. Thank you.